Hello everyone and welcome to the first seminar of the CHE 446 course. The topics covered by the problems in this seminar are broadly classified as Introduction to Process Control, the Control Block Diagram, Theoretical Process Modeling using the First Principles approach, and a Degrees of Freedom analysis. In question 1 of this seminar, we are asked to make a control diagram for a heat exchanger. The heat exchanger is used to cool down a hot liquid, shown by the red arrows, using a cooling liquid, shown by the blue arrows. We are asked to draw the control and instrumentation diagram, state the actuator, controller, and sensor, state the controlled, manipulated, and disturbance variables, and whether we can control the hot inlet temperature. For the given heat exchanger, the control and instrumentation diagram can be drawn as follows. In this diagram, a valve operates on the cooling water inlet flow rate. The valve itself receives signals from the temperature controller, which in turn takes measurements from the temperature sensor. Let us now identify the different components of a typical control block diagram in the current schematic. The actuator is the control valve that operates on the cooling water inlet flow rate. The controller is the temperature controller that takes in readings from the temperature sensor. And the sensor is the thermocouple that measures the temperature of the hot fluid outlet. Now let us identify the different types of variables in this schematic. The control variable in this control diagram is the temperature of the hot fluid at its outlet. The manipulated variable is the flow rate of the cooling water into the heat exchanger. And the disturbance variable is the temperature of the hot fluid at its inlet. In the final part of question 1, we are asked if the control diagram we have devised is capable of controlling the inlet temperature. This current schematic is representative of a feedback control system in which the hot fluid outlet temperature is the controlled variable. The heat exchanger is able to influence the temperature of the hot fluid at its outlet, but not that at its inlet. Therefore, we cannot control the hot fluid inlet temperature using the presented control schematic. However, we can measure the inlet temperature and possibly control its temperature upstream separately. Let us now move on to question 2 of the seminar. This question involves the process modeling of the given setup. We are given a closed stir tank reactor that is divided into two compartments through which both material and heat can be exchanged. There is no heat loss between the reactor and its surroundings. The second compartment has a cooling coil built in to remove excess heat of reaction. The variables in the problem can be tabulated as shown. The problem itself comes with certain assumptions for process modeling as follows. The inlet flow rate and temperature into the compartment as well as the temperature of the cooling medium are variable quantities. UT and AT are the heat transfer coefficient and surface area between the compartments, and UC and AC are the heat transfer coefficient and surface area of the cooling tube. The liquid volumes of the two compartments are V1 and V2 respectively, and they remain constant. There is perfect mixing in both compartments. The density and heat capacity of the reacting fluid are constant, and there is no heat loss to the surroundings. In this question, we are asked to perform the following tasks. To develop a dynamic model for this process to determine the temperatures T1 and T2, as well as to perform a degree of freedom analysis for the model and to identify the parameters and variables. Let us begin by constructing the dynamic model for the reactor system given. We start with the total mass balance for compartment 1. Using the law of conservation of mass, rate of change of mass within compartment 1 of the reactor is equal to the difference between the rate of mass flow into and out of the compartment. The problem statement mentions to consider volume to be constant, and therefore, we have volumetric flow rate into compartment 1 equal to the flow rate out of the compartment. This is equation 1 of the dynamic model. Now let us conduct an energy balance for compartment 1. Using the law of conservation of energy, we have the rate of change of energy within the compartment equal to the difference between the rates of energy flow into and out of the compartment, while accounting for the heat transfer between the compartments. Upon simplifying, equation 2 of the dynamic model gives the rate of change of temperature within the compartment 1. Similarly, let us conduct the total mass balance for compartment 2. Using the rate of conservation of mass with the constant volume assumption, we have the volumetric flow rate into compartment 2 equal to the flow rate out of the compartment. This is equation 3 of the dynamic model. Finally, let us also conduct the energy balance for compartment 2. Using the rate of conservation of energy, we have the rate of change of energy within compartment 2 of the reactor equal to the difference between rates of energy flow into and out of compartment 2 while accounting for the heat transfer between compartments 1 and 2 as well as the heat removed by the cooling medium. Upon simplifying, equation 4 of the dynamic model gives the rate of change of temperature within compartment 2 of the reactor. And therefore, equations 1 to 4 constitute the dynamic model for the given system under the listed assumptions. Therefore, the dynamic model of the reactor system can be represented by equations 1 to 4 that correspond to the mass and energy conservation equations. Let us now conduct a degrees of freedom analysis for the system. As we have seen, the dynamic model of the system contains 4 equations. Furthermore, we have the following classification of parameters and variables in the model. In this system, we have 3 input variables, that is Ti, Tc, and Q0, and 4 output variables, T1, T2, Q1, and Q2. Therefore, we have to specify 3 inputs to determine 4 outputs uniquely. The total number of variables in this system equals 7, and therefore, the degrees of freedom of the system is given by the number of variables minus the number of equations and is equal to 3. Alternatively, we can simplify the dynamic model given by equations 1 to 4 by substituting equation 1 and 3 into 2 and 4 to get a simplified dynamic model that is represented by equations 1 starred and 2 starred. Conducting a degrees of freedom analysis for this model, we have the number of equations equal to 2 now. We have the same parameters in the model. However, the number of variables is reduced. We have 3 input variables and 2 output variables. Here, we need to specify 3 inputs to uniquely determine 2 outputs. Therefore, the total number of variables in this new system equals 5. And the degrees of freedom of the system remains constant, that is equal to 3. Let us now move on to question 3, which is also a process modeling exercise. In this question, we have a jacketed stirred tank reactor as shown in the figure, and we are asked to derive a dynamic model for the system. There are a number of assumptions that the problem statement asks us to make for the purpose of process modeling. We assume that the materials in the reactor as well as the cooling jacket are well mixed and have constant volumes. We are also given the reaction rate equations for compounds B and C. We are told to neglect the heat transfer through the reactor and jacket materials but to consider the heat transfer between the contents of the reactor and cooling jacket, and to also assume that the material's physical properties remain constant. Here we have a list of variables in the system, as well as the notations for the parameters subject to the assumptions made previously. Rho depicts the densities, U is the heat transfer coefficient, A is the surface area between jacket and reactor, C is the heat capacity for reactor material, and S is that of the coolant. Ma, Mb, and Mc are the molecular weights of compounds A, B, and C respectively. V is the volume of reactor material, and Vc is the volume of the jacket. Let us begin by constructing the dynamic model for the reactor system given. We start with the total mass balance for the reactor. Under the law of conservation of mass, rate of change of mass within the reactor is equal to the difference between rate of mass flow into and out of the reactor. Since the problem statement mentions that volume is constant, we have the volumetric flow rate into the reactor equal to the flow rate out of the reactor. This is equation 1 of this dynamic model. Similarly, we conduct a total mass balance for the cooling jacket. Using the constant volume assumption, we have the flow rate into the cooling jacket equal to the flow rate out of the jacket. This is equation 2 of the dynamic model. Let us now conduct a component balance for compound A. Using the law of conservation of mass, we have the rate of accumulation of compound A inside the reactor equal to the difference in flow of compound A into and out of the reactor, accounting for its disappearance due to reaction to form B. Equation 3 of the dynamic model gives the rate of change of concentration of compound A in the reactor. Similarly, we conduct the component balance for compound B. Here, we account for the generation of B as well as its disappearance through two separate reactions. We also conduct the component balance for compound C, accounting for its generation inside the reactor. Now we conduct the energy balance for the reactor. Using the law of conservation of energy, we have the rate of accumulation of energy in the reactor equal to the differences in the rates of flow of energy into and out of the reactor, accounting for heat loss to the cooling jacket as well as heats of reaction. Therefore, equation 6 represents the change in temperature, or rather rate of change of temperature, inside the reactor. Finally, we conduct the energy balance for the cooling jacket. Here, equation 7 represents the rate of change of temperature in the cooling jacket as the difference in the rates of energy flow into and out of the jacket, accounting for the heat taken away from the reactor by the cooling fluid. Let us now conduct the degree of freedom analysis for the system. We have 7 equations as seen and 13 variables as tabulated, out of which 6 are input variables and 7 are output variables. Therefore, we must specify 6 inputs to uniquely determine 7 outputs, and the degrees of freedom for this system under the given assumptions is 6. So this brings us to the end of Seminar 1. Thank you for your attention and feel free to reach out with any questions.